All right, here we go. We are going to take some more notes on remainder theorem. So here is the remainder theorem. You do not need to write it down because we wrote it down last class, but this is like a different version, same thing, written a different way. When a polynomial p of x is divided by the linear factor x minus a, then the remainder will always be p of a. So plug in the solution to get the remainder. And then there's like, it's written in the same form down here. This is actually saying what this just said. Okay, so the solution is a, x equals a, because it comes from this factor. X equals positive a, flip the sign, and that's why we plug in positive a into p. P of x was being divided. Okay, so if you get something that looks like this, we can find the remainder. This is the remainder, right? The part that's on top. We can find the remainder just by plugging in the opposite of what it's being divided by, like the solution of the factor that it's being divided by. P of a is the remainder. Okay, so really quick, I want you to look at this warm-up. You're going to give me two different ways that I could solve this problem. So if the ratio x squared minus 11x plus 22 divided by x minus 9 was placed in the form q of x plus r over x minus 9, and really quick, what does r stand for? What does r stand for? The thing that's on top. Tell me, please, what does r stand for? All right, r is the remainder. So where q of x is a linear function, so q of x is a linear function, which of the following is the value of r? So it's asking us, what is the remainder? It's asking us, what is this remainder? Give me two different ways that I could solve this problem and find the value of r. We have two possible ways, and I want you to give me both of them, or your ideas. Go. Okay, so the first way that we could find the remainder is divide. All right, we could divide and then see what we get for the remainder. Do this division. Or the second way that we could find the remainder is plug in the solution. Really quick, we're going to look down at what we're dividing by, and the solution is going to be what x equals. X equals, flip the sign, positive 9. So to get the remainder, we could plug in positive 9. Plug in positive 9 into the top function, the numerator, to get the remainder. Okay, that's what the remainder theorem says. So let's do an example, and then we're going to get a lot more practice today. Sweet. Here we go. Write down this entire example, please. It's a 3-part question, so you can go ahead and work on writing down both parts 1 and 2. All right, consider the polynomial p of x equals x cubed plus kx squared plus x plus 6. Find the value of k. All right, so really quick, I'm going to make note. We're trying to find this so that x plus 1 is a factor of p of x. Okay, so really quick, we're going to write down a note. We want x plus 1 to be a factor. And we took a note last class that said, if something's a factor, what's the remainder? If something is a factor, comma, remainder equals what? Tell me, what does the remainder have to be for something to actually be a factor? Something being a factor means that it's divisible. It goes in evenly. If something is a factor, it goes in evenly. So what would your remainder be? Go. Okay, remainder needs to be 0. If something is a factor, we need the remainder to be 0. So we need the remainder to be 0. We know that. And then how would we find the remainder? How would we find the remainder if we want x plus 1 to be a factor? What would I plug in? What would I plug in to p of x to find the remainder? Please tell me, what would you plug into p of x to find the remainder? Go. All right, if we're using the remainder theorem, we're going to plug in what x equals. X equals, what does x equal? Flip the sign on this factor, -1. So plug in x equals -1. That's going to give us the remainder. So let's do that really quick. P of -1 equals, put parentheses every time you plug in -1, put parentheses around it, plus, okay, k stays k. We're plugging -1 into x, right? So k stays k, so let's leave that k. Then we have -1 squared plus -1 plus 6. All right, we have needed some simplifying based on what I've seen, some simplifying practice. So let's just break this down. -1 cubed is -1 times -1 times -1. This turns into +1, but we still have times -1. So equals -1. Anytime you have a negative to an odd power, it's going to come out to be a negative still. So -1 cubed is -1. I'm going to erase all this and put -1. All right, we have -1 plus -1 squared is -1 times -1. That's just +1. So we have k, and if you want, you can write times +1, but you'll see that we won't need that. And then +1 plus -1 is going to turn into -1 plus 6. So let's go ahead and make sure we know this is P of -1. All right. And then let's simplify even more. Equals -1, I'll highlight what I'm combining. -1 minus 1, that's -2, plus 6, that is 4. So we get k times 1, also y'all, k times 1 is just k. So we get equals 4 plus k. Sweet. P of -1 equals 4 plus k. What did P of -1 represent again? Someone, we need to know, what does P of -1 represent? So tell me, what does P of -1 represent? What did we just find? Go. We found the remainder. When you plug in the solution, you're finding the remainder. So the remainder is 4 plus k. But we also need the remainder to equal 0. We need the remainder to equal 0. We know that the remainder equals 4 plus k, so here's what we're going to do. We're going to set 4 plus k equal to 0. So let's bring these together. Whoop. 4 plus k equals 0. We're setting what we know is the remainder equal to what we need the remainder to be. Okay, and now let's solve for k. How would we solve for k? Inverse operations, -4, -4. K equals 0 minus 4 is -4. Done. All right, so let's go through what we did really quick one more time. To find the remainder, you plug in your solution to the factor. Then you get a remainder. And you set it equal to the remainder that they want you to have. We wanted to have x plus 1 be a factor, which means the remainder has to equal 0. So that's why we set the 4 plus k equal to 0 here. And then we solve for k, the missing piece. Okay, so if we're going to plug k equals -4 into p of x, let's go ahead and do that. We have p of x equals, we go back to the original equation, so I'm looking back at the top right here, and I'm just plugging in for k. So we have x cubed plus -4, that's going to be -4 x squared, because k is -4, plus x plus 6. Okay, that's p of x. Let's do a different example. Here's our second example. Find the quotient for p of x over x plus 1. Remember, the quotient is the answer to a division problem. So if you're still struggling with division, make sure you pay attention. I'm going to go through this quickly because we have done a lot of division already. All right, so the quotient, we're dividing. I need to draw a box. So I'm going to draw my box. And on the side of my box goes the factor on the bottom, x plus 1, what we're dividing by. Inside my box goes the numerator, p of x. P of x is right here. So I'm going to put x cubed. And then we have to reverse engineer for the outside of the box. So we have x squared. And then We know that 1 times x squared is x squared. How many x squareds do we see in our numerator? I see -4, so I need -5x squared. We get -5x, and then 1 times -5x, -5x. How many x's do I see in my numerator? Just 1. So I'm going to put 6x here, because -5 and 6, -5 and 6 add to 1. And then on top we get 6, because x times 6 is 6x. And then lastly we get 6 inside. Okay, did we have a remainder? Well, did we end with the number we needed? We needed 6 at the end. We got 6 on the inside. That means the remainder is 0. Y'all, didn't we just say in the problem above that the remainder was going to be 0 if we made k equal to -4? Yeah, we did. So, yay, it worked. We got a remainder of 0. We were supposed to get a remainder of 0. All right, last piece. Last piece, write this down. Factor the quotient from part B, or number 2, from number 2, to write p of x in factored form. All right, remember the factors of p of x are the pieces that multiply together to make p of x. Okay, so first of all, we need to take a step back and look at our box. Look at our box. We use the box for three main things. Is what we've used the box for in the past. We've used it to factor, we've used it to multiply, and now we're using it to divide. You can still think of the box as multiplication in all of those ways that we use the box, the area model. This box that we just did was division. The one that we just did right here, that was division, right? But we can think of it and look at it as multiplication. What are the two things being multiplied? It's the things on the outside, right? So, here's the crazy thing, y'all. P of x, the numerator. Where does that show up? Does that show up inside or outside of the box? Does the numerator appear inside or outside of the box during division? Go. All right, that shows up inside the box. P of x shows up inside the box. It's right here in blue. Outside the box, those things highlighted in bright blue are the two things that multiply together to make p of x on the inside. So, y'all, this is really crazy. We can write p of x, this pink thing right here, this pink thing can be written two ways. We can write it like this, like above, or we could say p of x is also equal to these two things being multiplied. So let's write it like that really quick. P of x equals x plus 1 and x squared minus 5x plus 6, because that was the answer on top to our division problem. If you multiplied these two things, you would get the inside of the box that we have right here, and it would equal p of x. Crazy, right? Okay, so these two things in pink are equivalent. They are the same thing. Now, this question is telling us to factor the quotient, factor the answer from number 2. The answer from number 2 is this. And then it's saying write p of x in fully factored form. So all that question is saying is factor more. Factor p of x all the way. We have one factor. One factor is right here. We need two more factors coming from this piece. So let's go ahead and do that. And we're going to use the box, which is how we factor. So I'm going to go ahead and draw another box, but one for factoring. And really quick, I'll just write this down here, equals x plus 1, x squared minus 5x plus 6. Okay, so this is p of x. We need to fully factor it. So we're going to factor the second piece, and I will highlight that. We're factoring this piece. So we need to multiply to a times c. So multiply to a times c, which equals 1 times 6, which equals 6. We need to add to b, which equals -5. That's my b value, right? All right. So now I'm going to make my little table thing. Things that multiply to 6. We have 1 and 6. We have 2 and 3, and that's it, right? which one of these can add up to -5? Well, we need it to multiply to +6, add to -5. So we're going to put negatives on the 2 and the 3, and those will be the two factors that we use. Okay, so inside our box, let's go ahead and put x squared, first term, 6, last term, and then the two things that we get that multiply, -2x, -3x, I put x's on them. Pull out a GCF. So we have the GCF on this line is x. The GCF on this line is 3. The GCF on, we'll deal with that in a second. GCF in this line is x. GCF in this line is 2. We have to double check, do they multiply to the right thing? X squared, yes. 3 times x, -3x, no. So that needs to be negative. But then -3 times +2, that would give me -6. So to get the right thing, we would have another minus. Okay, so this thing highlighted in green can also be written like this. The same thing, like this thing highlighted in green is also, it's the same as x minus 2, x minus 3. So now we can finally finish our problem. We can write p of x in fully factored form. P of x equals, these are the three things that multiply together to make the original p of x that we started with. X plus 1, don't forget that factor. And then we have these two, x minus 2, x minus 3. That is the same p of x that we started with in the very, very beginning. And then if we wanted to write the solutions, we would flip the sign. X equals -1, x equals 2, x equals 3. Yay! Okay, we are done with remainder theorem part 2. Now let's do some remainder theorem practice.